Okay, let me go ahead and get started. Okay. So I'm gonna try I know that last time I was muted for like the first 10 minutes, so that's telling me that I'm not doing enough interacting with the people on Zoom. So if you're on Zoom and you notice that you've asked a question on chat and I haven't answered it, feel free to unmute yourself and just get my attention, especially whenever there's a pause. Okay, so today we're going to do a little bit more of this sort of technical stuff, trying to understand the geometry and topology of decision boundaries and decision regions of feed-forward ReLU networks. But I'm positive we're going to get done with this part today, and then we'll start talking about transformers. So hopefully I'll be able to say at least some high-level things at the end of class today. Okay, so just to remind you where we are. So if you have a ReLU neural network, standard feed-forward ReLU network. And here we're thinking we've chosen some particular parameter in parameter space, the architecture. Then associated to each one of the affine linear maps, affine linear layer maps. So we have these layer maps, which are affine linear maps composed of this component-wise nonlinearity called ReLU. And associated to each one of those is a hyperplane arrangement, namely the zero sets of the corresponding output neurons. And last time we defined these, so we kind of talked about how now sitting inside of each of these layers, we have not only a hyperplane arrangement, but actually a whole polyhedral complex. So it's a whole decomposition of the layer into these polyhedral sets, which are essentially you know, the sets of the solution sets to finitely many linear inequalities. So these are these polyhedral sets, and that allowed us to construct this canonical polyhedral complex associated to the map for this fixed parameter. And we got it by pulling back. So for these piecewise affine linear maps, pulling back these, inductively pulling back these polyhedral complex and forming this formal level set complex. So this one's defined inductively. And I also made these definitions that F theta is said to be generic if all the hyperplane arrangements associated to all the layer maps are generic. In the classical sense of hyperplane arrangements being generic. Namely that every k-fold intersection of hyperplanes should be a affine linear space of codimension k. And then there was also this definition, this important definition. So F theta is super transversal. If for all layer maps, when you look at the composition of maps to the Lth layer, so this is now a map that is affine linear on cells of the canonical polyhedral complex constructed so far. And what you want is that it's transverse on cells to the polyhedral complex associated to the hyperplane arrangement in the L layer. So the idea here is that all the intersections of cells have the expected dimension. This ensures that so you need generic to make sure that in a single layer they have the right behavior, and you need the super transversal condition to ensure that between layers you also have that. So all intersections of cells have the expected dimension. This is the notation for transverse on cells. All right, so I'm now going to state a theorem carefully. So this is the first theorem. By Marsden. So if you have one of these ReLU network maps, and it happens to be generic and super transversal, then the assignment as from this polyhedral complex. So now whenever I write the script C, I just mean the canonical polyhedral complex for this particular ReLU network. So here, the cells of the complex are these polyhedral sets, which fit together, with their natural boundary maps. And here is the number of non-input neurons. And so now you have a natural assignment from the cell to -1, 0, or 1 for each non-input neuron. And that's actually coming from taking the sign of the pre-activation output. And the way that you do the assignment on a cell is you look at the interior points on the cell, and then you assign it that sign. So this is C. So for each cell C, you look at C and P, and the interior is C. I'm kind of P in the interior C, and you assign the pre-activation sign. So we have this notation. This is the alpha layer. This is the ith neuron in the alpha layer. So for each cell, you take a point in the interior of it, and then you compute its sign for each of the neurons.
Should P in there somewhere?
Yeah. And the theorem is that this is a well-defined and injective map of cells. Okay, moreover, so this is kind of stating formally what I said informally here. So you can look at the dimension of this cell, which is just the dimension of its affine hole. And it has codimension K. So this is dimension n0 minus K in this input space. It's codimension K if and only if the output of this map has K zeros. So the sign sequence, this ternary sign sequence has K zeros.
So this is basically saying that the maximal dimension cells are never zero.
That's right. That's one implication. Any other questions? All right, so that's the first really nice statement that somehow when you start labeling the cells by their signs, the label really matches the dimension of the cell in a way that you would expect. Namely that every k-fold intersection of bent hyperplanes, the pullbacks of hyperplanes from later layers are sometimes called bent hyperplanes or fold sets in the literature. And the statement is that if you impose these geometric conditions, then every k-fold intersection of bent hyperplanes is codimension K. Okay. All right, so that's the first statement. And then the second statement, which I think is really interesting statement, it's kind of the goal of everything that I've been saying over the past couple of lectures, is the following. So let's see hat be the CW complex. So now this is going to be in a one-point compactification of your input space. So just formally put point at infinity, and it's formally a face of every unbounded cell of your canonical polyhedral complex. So okay. So now for each neuron in your network, so for each layer L, and each neuron in the L layer, there exists a subcomplex of a cube complex. Well, it's a little bit more than a cube complex. So I kind of lied before, but it's not much more than a cube complex. So I'm going to call these CC plus LI, CC minus LI, and CC0 II. So these are going to be complexes, and they're contained in, as I advertised before, this n-dimensional cube union an n0 cell attached somehow along some part of the boundary of this. And in fact, the way that's attached along the boundary is determined by the labelings of the unbounded cells. Boundary of. And the point will be that the homology of these are chain complexes. These are CW complexes, which are naturally kind of sub-cube complexes of this cube complex. And the homology of each of these complexes, plus 0 and minus, with Z2 coefficients, is the same as isomorphic to the homology of this CW complex, this 1-point compactified CW complex here. You have to do some flipping of indices, but it's essentially the same complex. Degrees here. And it's coming from the fact that this complex is naturally graded by K cells that correspond to N0 minus K cells over here. Okay. All right, so right, and the point here, which I should just state explicitly, is that these complexes plus minus 0 are very naturally defined, and they correspond to the decision regions. Plus and minus are the decision regions, and 0, the decision boundary of the ith neuron in the ELF layer. I haven't said anything because I haven't defined anything, but about any questions about this sort of statement, at least like the outlines of it.
What's the dimension of the CLI path of the CLI plus 0?
Right,
It's a
so
complex,
these are
right?
sub-complexes that are, yeah, they are no more than N0 dimensional.
Sure, but
Yeah.
that's just they're sitting inside of it.
That's right, that's right, yeah. So these guys are always sitting inside an N0 dimensional subcomplex of this cube complex. Because the cells are naturally given by these signs. There's the sign map that I erased, but. Okay, so I'm not gonna, I'm gonna sketch the proof. At a level that will hopefully convince you that the statement is true. And then I'll do an example, a carefully worked out example. Okay, so here's the sketch of the proof. And actually, I'm only going to sketch the proof of theorem B. Theorem A is somehow not as hard. Theorem B is really where the interesting stuff is. This construction. Okay, so let's construct the the one compactification. And you're adding a 0 cell at infinity, and you're treating it as a face of each unbounded polyhedral set. So you're doing this so that now you have a realization of SN0 as a CW complex, because each of the cells is a polyhedral set. So it's just a ball, it's just a cell. So you can treat this as a CW complex. So each polyhedral set. So this is a cell. Which is a ball of the particular dimension. Some dimension. So each cell have this complex, like I said, is homeomorphic to a closed disk. Dimension equal to its dimension as a polyhedral set. And the face maps are coming from the structure as a polyhedral complex. So each of these polyhedral sets has faces, and the codimension 1 faces are the facets, and these are the boundaries in this boundary map, or the images of the boundary in the boundary map. Okay, so if F is generic and supertransversal, then you have this map which assigns to each cell of the complex before you compactify. Some sign, some collection of ternary signs. So I'm C to S of C. And now what I claim is that you can now assign to each sign sequence some, now we have some map, which I'm going to call RN. I probably overused R, but this is now, if we let I be the closed interval from -1 to 1 viewed as a cell complex itself. So it's got 1 cell and 2 0 cells on the sides. So now we have a map to IN. And here's how we're going to define it. So I'll just define it for each term. This is actually a product of terms of the form R. So we're thinking of this as being a cell complex here. And what we do is we send -1 and 1 to the 0 cells. So it's kind of exactly what you might think. You send -1, -1, +1 to +1, and 0 to the 1 cell. So now if you have a string of these, you're gonna construct a cell of dimension k if you have k zeros by taking the product of those cells inside of here. So now product of these maps. So this is a product cell complex. So if you have some string of negative ones, zeros and ones, you would send it to the product of those. So for example, if you had like negative 1, comma 0, comma 1, comma 1, or negative 1, you would just send this to negative 1 cross. Negative 1, cross. And this sits naturally inside this 2, 3, 4, 5 dimensional cube. And this is one dimensional inside there. It's the interval sitting at this level. Questions about that? So, moreover, again, because of the transversality, 0 minus k cell in C is sent to a k cell. In this chain complex. Okay, so actually I haven't quite specified how you define the chain complex associated to, L comma I, the ith neuron, the Lth layer. But for that, you just notice that each one of these is defined by either, having a +1 or a -1 for that neuron. So I probably should have said this carefully. So this is the so as a set. And C, for which S of C, I guess in the Lth ith position in the string is equal to +1, 0, or -1. Okay, so you have some, you have your coloring of your cells by these ternary labelings, and now you pick out the cells that have the ternary labeling +1 in this position, and that would define this subcomplex. And moreover, let's see. C prime is a co-facet of C in your original complex. If and only if when you apply this, when you take the sign, the ternary sign, it's obtained from S of C by replacing a single zero with a plus or minus one. So I'm not quite finished arguing, but I think it's time for me to draw a picture. Because I can't quite finish arguing without a picture, I think. Let's just carefully draw this picture.
Now, when you say, am I supposed to read that as C prime as a co-facet of C? Or what is the co in parentheses there?
Yeah, I guess C is a facet of C prime.
Okay,
Is how you should read that.
okay.
I think everything will get clear with this example. Somehow everything else is just words. I'm gonna I've drawn this particular picture a lot of times, but I'm now gonna actually label more things on it. So this is a polyhedral complex associated to a network of architecture R2, R3 to R1. And here, just to note that it's the pullback of that neuron that's in green, or the zero set of that neuron that's in green. And I'm gonna just start. I'm just gonna start labeling so there are four non-output neurons in the network. So I should be able to label each of these regions with 4 tuples. And let me just use plus, minus, and 0. And I'm going to kind of separate them in terms of layers. So this top dimensional cell is plus, plus, plus. Well, I'm going to do the first layer first, and then I'll do the second layer. Because remember, you're gradually getting subdivisions of your polyhedral complex as you add more layers. So let's do the first layer first. This is out here, this is plus, plus, minus. Plus, minus, minus. Plus, minus, plus. Minus, minus, plus. Minus, plus. Here it's minus. Those are the signs for suitable choices of weights on these. Basically, you just need them to all be pointing in here. These would be the sign patterns for the first layer map. And then I'm not going to draw everything, but for example, this one cell, before you put in the green, would be labeled with minus, plus 0. So before you put in the green, this is a co-face of this. And you notice that you realize that from this by changing one of the zeros to a minus.
So there's no minus, 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 and no 0, 0, 0.
there is no 0, 0, 0, and there's no minus, minus, minus. So this map S is very far from surjective in general. Questions? So I just labeled a few things, and now when you put this green thing in, then each of the regions, not all, but many of the regions here get split into two. So on this side, say this would be minus, this would be plus, and that would be the same for everything you see in here. The initial 3 tuple is the same. Great. And so now let's write down let's describe the subcomplex for this final neuron. So let's describe the second layer, first neuron. This neuron. Okay, and so I can't draw a 4-dimensional cube complex, but I can draw the vertices of 2 3-dimensional cube complexes. Sorry, the vertices of 2 3-dimensional cubes. And so these are all the ones that have 1 plus 1. So like plus, minus, 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 plus, minus, 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 etc. Oh, actually, I should probably label them the same way I have on my page. So I get confused. I'm calling this minus, minus, plus, minus, plus, minus, plus, minus, minus. And I'm going to call this minus, plus, 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 minus, plus, and plus, plus, minus, plus, plus, plus. So these are like the vertices of a cube, a 3 cube. And I have 2 copies. So I'm thinking of this as being the copy at cross plus 1 for that final neuron, and this is minus 1. That associated to that final neuron. Okay. And now, if you look at the cells along these, along this neuron, so this is the 0 set. So I'm wanting, so for example, this one is, sorry, this is the plus, minus, minus 0 in that final neuron. So this is going to pick out some path here, like this. This is actually the boundary of the, so in this position, you have a -1 to 1. So this path that we see here is actually one of the boundaries of that one cell. So these, right. You have, so for example, this cell is +1, -1, comma, -1, comma 1. So this cell goes to +1, -1, -1. Let me actually use the notation I wrote down before. Okay, so in this 4 cube, what you see is this interval. And you have such an interval for each of these points. So that I guess is the interval associated to +1, -1, -1 is this one. Okay, so that's this one cell here. It gets mapped to this interval sitting over with boundary here and here. Okay, so I'm going to draw the same picture down here. And you might be wondering what these 1 cells are here. Well, those are, again, 1 cells cross this interval. And those are corresponding to the 0 cells. Because for those 0 cells, you have now another interval. And you can see that if you now, look at what this object is, it's just a circle. I mean, it's a thickened circle. Which has this, it's, yeah, really somehow there's actually a homeomorphism between these complexes. But that's not the way that she states it, but that really is the case, that, well, it's not a homeomorphism. It's like it's a homotopy equivalence. I mean, so actually the way that I think it's best to think about this is to just thicken everything. Okay, so thicken everything. But actually what you have now is a geometrically dual complex. And that actually is the complex that you're constructing over here. So when I say geometrically dual complex, I mean, this is like an interval cross an interval. Yeah, so inside of this 2 cell, you could instead think of it as a thickened 0 cell. And now the faces of that thickened 0 cell are the boundaries of the thickened 1 cells, etc. And so this duality is showing up in the boundary maps in the 2 regimes. But the point is that the face structure here corresponds to the co-face structure there. And so you also have to do some flipping of the indices, but it all works out. And the homology groups here correspond to the homology groups there. Questions about that? Is it somewhat convincing? It really does work and it's really beautiful. So yeah, the point is that you can now enumerate for these generic supertransversal parameters, you can now enumerate all of the, so she actually proves that you can actually construct the whole complex just by knowing the vertices. So algorithmically, just by knowing the vertices, she can construct the whole complex in the case that it's generic and supertransversal. And then she actually has written a program to compute the homology groups. And so she can see, for like a random parameter, what are the homology groups, what happens during training, et cetera.
By vertices, you mean things that are vertices in IN or the things that are
Vertices over here, yeah, vertices over here. So she just has to compute the signs for the vertices, and that determines, am I saying the right thing? Yeah, I think that she just has to compute the signs for the vertices, and then she can reconstruct the whole complex from there. And and then compute fees.
And is the point there that you just need, sorry, the list of vertices, I mean, because you might imagine over here, well, of course, you need the vertices and you need to know how they're all connected to one another. But is the point that just from the set of vertices?
I think she reconstructs everything from the set of vertices and, she has in advance an ordering of the neurons in some particular way, and then, she lists the vertices and their ternary activation patterns. And then from there, she reconstructs the whole complex.
You can draw the cells by just looking at which things are almost the same.
Yeah, exactly, that's right.
What does the homology tell you in terms of the deep learning outcomes, or like the outcomes of the network?
Yeah, I don't know. I don't know what it's useful for, but I think it's really pretty. And it's a good introduction to the geometry of ReLU networks to kind of start with this. I mean, I kind of hope that they would provide, that the topology would provide abstractions to certain types of things. And so, yeah, it's kind of a hammer that doesn't have a nail yet, I think.
Ellie, have there been any patterns found in how the homology might change during training? Like, does it become more complicated or have more components?
Yeah, I mean, if your data has, has some kind of natural homology, if your data set has some natural topological structure, then it will be learned during training. But one really interesting thing that she found is that at initialization, the topology of, all decision regions is just like as simple as it could be. The homology groups. And there's not really an explanation for that. There's no theoretical explanation for that. That's all. That's just empirical. Okay. All right. So I think I'm gonna stop with this now, and I'm just going to, the rest of class today, I'm just going to kind of give you a little bit of an introduction to transformer architecture, but I'm not going to actually say anything in detail about the transformer architecture. I'm just going to give a kind of high level view, and then I'm going to tell you a little bit about finite state automata. Yeah. So GPT. So GPT stands for Generative Pre-trained Transformer. What is such a model good for? Well, it's good for predicting the next item in a sequence out of a finite list of items. Okay, so let me tell you just kind of broadly speaking what the transformer architecture generally is, just as a kind of like a bird's eye view of it. So I think it's a composition of ReLU networks, but with some extra connections called skip connections, equipped with what you might think of as a routing system, which are called attention heads. So I'm just going to write that down so we can have something in mind. So these ReLU networks are kind of exactly the biggest building blocks of transformers. But the attention is a really important feature of the transformer. that we'll get into in detail later. What are called residual or skip connections. So the idea here is that just like the class of functions that we've been talking about, this is a parameterized class of functions. Is somehow, in that sense, not much more, not much more than we've been talking about. So for each parameter, it kind of defines the entries of the various matrices that are involved in constructing this. And there are these blocks which are multi-layer perceptron blocks, which are typically neural networks with ReLU activation. And these skip connections are, I'll say much more about that later, but so far we've just had maps between layers, between adjacent layers. But now you might start constructing maps between non-adjacent layers. You still have this feed forward architecture, but now you can skip. And you can skip kind of as far as you would like. You put in all of the skip connections. So it's starting to look like,
So those are different maps, it's not.
different maps, yeah, different maps. So before I say, what did I do with my others? Before I say much really about this architecture, so I'm not going to say anything about this architecture beyond this today. I'm just going to talk about the task that it's performing. Okay, so as I said, these architectures, what they're used for, essentially is predicting the next token in a sequence of tokens. And so we're familiar with using say ChatGPT or GPT-3, GPT-4 to predict the next, say, word in a sentence, or actually to predict a whole a whole output from a whole input. But really what it's doing is literally predicting each word that comes next. So I'm lying a little bit there. Tokens in language are actually smaller units than words, but we may as well think of them as words for what we're doing. Okay, so you have a big bag of words in some language, and what it's doing when it produces the output is actually just choosing the next word each time from the string that it has so far. So token is sort of the basic unit of language. So think word, if you like. And now if you have T, the finite set of tokens, the task of one of these generative pre-trained transformers. So if you're given now some ordered sequence of tokens, predict UK +1. And what the model does is assigns a probability vector of length, the size of the set. So this sort of parameterized class of functions is taking, say, length k sequences of tokens. And now for each parameter in the parameter space, so omega is always in my class representing the parameter space. You assign one real number between 0 and 1 to each of the tokens in your corpus, your language. And this is a probability vector. So it sums to 1. So the output will be the token that has the highest probability. Okay, and you now do the standard thing. You train on a huge corpus. You train on a huge collection of strings in your language, where you X'd out the last token in your string, and then you put that as the label. And you encode it as a one-hot probability vector. So, again, it's like input-output pairs for a supervised learning problem. The inputs are these length k strings of tokens. The output is, you put a 1 at the position associated to what you know to be the next token, and a 0 everywhere else. And that's what you train on. Okay. And now after training, you can use this model on new strings to predict the next token. Is that clear what you're doing? I mean, I haven't told you how to associate to a parameter some gadget, but essentially what we're doing is exactly the same sort of thing. Okay. So just in my last few minutes of class, last 15 minutes of class, what I'm going to do is just kind of warm up. So by telling you about one computational model that is actually reasonably powerful that you might try to look for in transformers, and maybe at least in certain sort of very limited settings, this is a reasonable model for how we predict the next token in certain situations. There's a classical model of computation called a finite state automaton. And it's a really rudimentary model of computation. But it's reasonable to ask whether, at least in certain situations, something like a transformer architecture would be implementing something like this. For a different task like this. So, I mean, somehow I think that there's a belief that that underlying what's going on with something like a transformer is actually that there's some hidden state in the the model is representing, that when it gets say the last token, that state changes and you enter a new state. And once you're in that new state, then you know what that next token should be. So somehow this is a model of computation. Again, it's completely rudimentary and it's almost certainly not going to tell the whole story here, but I think it's a good story to tell as sort of a first pass. And it's very likely, for example, that tokens often usually complete to like words, and so there must be something like kind of deterministic happening there in many settings. So you might believe that these are modeled somehow from the transformer architecture. Okay. So what is a finite state automaton? Well, it's very simple. It's a quintuple of states, updates, outputs, and two maps at an H. So S is just a set of finitely many states. I think for some reason I'm borrowing notation from a particular paper, so I'm just going to match that. So you have S states, finitely many states, finitely many updates. And finitely many outputs. Then F is a map that takes in a state and an update, and it gives you a state. H is a map that maps from states to outputs. This is the update map. So an automaton is a very first way that you might approach like a multi-class classification problem. So if you have, I didn't write down this outputs. So what you might want to do is predict from a string from an initial state and a collection of updates, a class among K classes. And what you do is you take your initial state, and for each element of the string of updates, you now apply this map F to the pair to get the new state, and then you follow it to the end, and then you apply this output map to get the class. So let me just give a very simple example of this. So for example, modular addition, modulo any positive integer is a finite state automaton. So it's useful to model finite state automaton by modeling the states as vertices and the U's as edges between vertices. So, for example, mod 3 addition, where I'm labeling my states obviously by the modulus, sorry, the remainder. Like this. And then you might do a decision problem on this automaton. Namely, the decision problem might be, is the sum of these numbers mod 3 divisible by 3? And that can be represented by this. So you have this output map H. So this is divisible by 3, but these aren't. So this is a really simple representation of mod 3 addition as an automaton, finite state automaton.
Hey, Ellie, it's a little hard to see what the last three numbers you just drew, +1.
Yeah,
-1.
+1 and -1, yeah.
Okay.
So yeah, I'm just thinking of that as being +1 is yes, it's divisible by 3, -1 is no, it's not divisible by 3. So in this case, our states would be 0, 1, and 2. You know, Q0, Q1, and Q2 represent 0, 1, and 2. Our updates are also 0, 1, and 2. Our map is, you know, add them mod 3. And then H, so this is +1, -1. And the output here is defining, is the state divisible by 3. Yeah. I mean, I'm not being really super careful here about how I say all this, but so this is H. Okay. I mean, another, you know, what's cool is that actually there are a lot of situations that are modeled by finite state automata that you might not expect. So I'm just going to give one more example, although it's not going to be a complete example, but I think it's useful to know these kinds of things if you are a mathematician interested in computation. So another example, less trivial example of a finite state automaton is the word problem and certain finitely presenting groups. So there are certain groups in which the word problem, i.e. if you have some word in the generators, it's decidable whether or not that word represents the trivial word. For general groups, this is not decidable, but for certain groups it is. And in fact, I'm not going to say much more about this besides referring you to a really, I think, beautiful book called Word Processing in Groups. And I don't remember all the people in the list of people who wrote it, but Epstein is one, and another one is Thurston. Bill Thurston. And in fact, he characterizes the groups that have, for which the word problem is decidable using a finite state automata in terms of the geometry of the group, which is really, really beautiful. So one example of such a group is the braid group, which I've mentioned before. So it turns out there is a finite state automaton that determines whether or not a braid word is trivial, which is really cool. So the updates are the generators in the braid group. The states are more complicated to describe, but this is really beautiful. This kind of thing is really beautiful, I think. So it can be a word problem for the big group. So these are actually like somehow remarkably powerful, even though they're really rudimentary. Do I want to say anything else? Maybe the last thing I'll say, because I probably won't say much more about finite state automata, is that it's a classical result in the subject. And this goes back to Lean in the 1950s. There's a nice paper of Siegelman in 96. And I probably should write like Sontag, Minsky. Anyway, there were a lot of people back when people were first looking at sigmoidal neural networks, trying to model finite state automata using sigmoidal neural networks. So the classical theorem is that every finite state automata, right, state automaton can be simulated by a recurrent neural network. And this means kind of exactly what you think it might mean. Namely, that there's an encoding of states as vectors in some vector space, and an encoding of updates as vectors in some vector space, in such a way that you can now realize both the update map and the output map as neural network maps. And this is somehow, their constructions are somehow not hard. But I guess what I'll end with, since we are getting to 3:45, what I'll end with is that I think what we've seen maybe so far in this class in terms of these kinds of results, that you can represent things using neural networks. You can represent computations using this structure of map. It doesn't tell you anything about whether or not that construction can be learned. So, you write down some parameters, you build this thing, but now you go out into the wild and you're trying to learn this finite state automaton. Will it ever actually converge to the solution that you came up with in your brain? And that's the kind of question I feel like not actually as much is known as would be nice to know. How pervasive are these, I don't know, the constructions we come up with in our brain are almost certainly not the things that are learned, for example. Even when they are learned, even when automata are learned in practice. Okay, so I'll just end there for today, and we really will start with transformers next time. And I'm, go ahead. Oh, I was just going to say that I'm heading back to BC for Jordy Williams's third talk. If anybody wants to watch a ride with me, you want to get a ride back later? Yeah. Okay.
Can you say what in this context the recurrent neural network?
Yeah. I mean, it's yes. Yeah. I mean, I meant to say more here, but I'll just write it down. So recurrent neural networks are basically like dynamical systems. So in this case, you'd have like a space where your states are encoded and a space where your updates are encoded, and then a map to the state where your space where your states are encoded. And you want this map to work no matter what the state and update is. So it's like you have the single map F, which is of the form of the neural network. You might have more layers here, but it's just that single map. And so if you want to see like a sequence of states from a sequence of updates, you unroll it and you use the same map each time. So you don't have a bunch of different maps, you have the same map that's being used again and again. Okay, awesome. Thank you guys. See you next week.